us and try to share?
Hey, yeah, I'm here. Can you hear me?
Yes, yes.
Okay, I'll start sharing now.
Okay.
Okay.
Right. If you can make it full screen.
Yeah.
Okay, great. Okay, so welcome back to the second morning session today. So next speaker is Chris Murphy on the Dimension-8 operators in SMEFT and left. Please go ahead, Chris.
Great. Thanks for the opportunity to speak. Yeah, so I'll be talking about Dimension-8 operators in the SMEFT and the left. And we heard a bit about this in the earlier talks in this session. So I'll be giving my take on it. This work is mostly based on a couple papers that I had out last year, and then a bit towards the end of the talk, I'll also talk about some slightly older work I had with Sally Dawson. Okay, so people might be wondering why are we bothering with Dimension-8 operators? Maybe some people are even asking. I've heard there's already a lot of Dimension-6 operators, so why do we have to go to this higher dimension? And so I guess what I'd like to try to convey is that there's really a lot of different physics that's happening at Dimension-8. So this combined with the null results so far from the LHC is increasing the motivation to search for new and different processes, and there's a lot of that going on at Dimension-8. I tried to convey this in this diagram here. I'm sure I've missed stuff. Feel free to ping me if you think of something. So there's many reasons why at Dimension-8 you might expect effects here that could dominate over Dimension-6. In certain cases, there's just no Dimension-6 operator that can generate the physics. An example of that is neutral triple gauge couplings. In other cases, in various diboson or boson and gauge boson, Higgs boson production, the interference from Dimension-6 is suppressed with the standard model contribution, and so you might have some Dimension-8 pieces that are the leading terms that you might see. In some cases, the only way you could get a Dimension-6 effect is correlated with another measurement, and that other measurement is highly constrained, and so it's only the Dimension-8 case that's unconstrained, and non-standard neutrino interactions could be an example of this. As we heard in Jiang Hao's talk, there's only two independent dipole moments at Dimension-6, and this correlation is broken by Dimension-8 operators. More generally, there's various Dimension-6 operators that have correlations that are broken at Dimension-8. And then another thing that's become very popular recently are positivity bounds. So I'm hopefully giving you a sense that there's a lot going on here, and it is worth studying this. Okay, but to actually study this, we need bases of operators. And again, we heard about this a bit in the more than a bit in the first sessions in this session. So the operator counting program has been hugely successful, but we want to go beyond that now. And so what we know from the operator counting program is that this is not a trivial task because there's a large number of operators. But there's other complications as we heard about before. There's derivatives and there's repeated fields, and this can complicate things. So in contrast with the talks you heard earlier, I'm taking what's called the traditional approach to this. I think this new method has probably put the traditional approach out of business, but this is how I did it. So I'm going to try to give you a summary of my thoughts on this process and how I went through it in the next handful of slides here. So there'll be some overlap with what we saw in the previous talks, but this is more of the traditional approach. Okay, so the first thing you have to worry about are operators with derivatives, and so there could be redundancies here due to the equations of motion. And so this problem has been solved a few years back by Lehman and Martin. And so what you want to do here is only keep the highest weight Lorentz representations. So if you have some derivatives acting on a field, you want only the maximally symmetric combination of their Lorentz indices, which are the Roman letters here on the lower left side of the screen. So in addition to the equations of motion, there's also integration by parts that you have to worry about. And so in constructing my basis, I followed the method proposed in this 2018 paper. I'm going to walk you through an example with the field content shown here and two derivatives. So it turns out that there's 4 candidate operators you can construct in this case, different ways of assigning the derivatives that do not induce the equations of motion. And those candidate operators are my x's on the right side of the screen here. So there's also another set of not operators, but Lorentz covariant objects. So these are the y's here. So these are gauge invariant. They have the same field content as the candidate operators, but one fewer derivative. And so the integration by parts constraints can be described as the derivative of this y object must vanish. And in this particular example, it turns out there's 3 independent integration by parts constraints. And so, so in this simple example is 4 minus 3, we only want to keep one of this combination of x's in our basis. So the other thing you have to worry about are repeated fields and their flavor representations. And in constructing my basis, I used methods based on this 2019 paper and its associated Mathematica package sim to int. And so the example I want to work through here, you could think of this as being relevant for radiative proton decay, so maybe proton to positron, pion, photon. And so I think this example highlights kind of all the different issues that could occur in dealing with repeated fields. So to start out here, we have our gauge groups and our Lorentz groups, and these are forming the rows in this table here. And then for each group of fields, you could break down how those that field or fields transform under the gauge and Lorentz groups. And what I'm also showing here is the permutation group of M objects, where M is the number of repeated fields. So it's S3 for the Q, and then trivially S1 for the lepton and the hypercharge here. And that'll be important in just a second. Okay, so to get the valid operator contractions, in terms of given this field content, what sorts of Lorentz and gauge contractions can we have? You multiply the rows together and find which of these Young's tableaux survive. And so I'm just gonna cross out the ones that do not survive in this case. And then there's one other condition I need to get the flavor representations, and that's you have to remember, just keep in mind that fermionic wave functions overall must be antisymmetric and bosonic wave functions must be symmetric. So for the Qs here, I have a completely antisymmetric Young tableau here. Same thing for the lepton, although that's trivial in this case. And so then what I do to get the flavor representations is instead of multiplying the rows, I'm now multiplying the columns together. So there were 2, sorry, I should back up for a second. There were 2 surviving Lorentz representations in this case, in this SU2 little l here. So I've colored them in blue and red, and so they lead to different combinations of flavor representations when you work through this here. So what's going on is there's the same Young tableau as the gauge and Lorentz representations, but now when I'm doing this decomposition, I'm considering it as the permutation group of M objects. And so one other sort of point of interest I found in doing this was that in some cases, starting at dimension 8, some of these flavor representations can vanish when there's only one generation of fermions. And that's what happens with this this red operator here in the bottom row. So in a Warsaw-like basis, dimension 8 is the lowest mass dimension where this occurs in the SMEFT. So a question could arise here as, so I've put this large round braces around the blue the blue flavor representations here. And so what is my motivation for doing that? So I just want to kind of briefly introduce this concept of Lagrangian terms. I don't want to get too involved in it. But so when I think about an operator, I would say an operator has definite flavor representation. So you might have 4 electrons like in this top row here. And then there's an associated Lagrangian term with this operator, which is some sum over operators of this type with different flavor, generally with different flavor representations. And so then the question becomes, what should be included in this sum? And that's really not a physical question. It's really up to your convenience and what you're hoping to do. So in my basis, I chose to go with the minimum number of Lagrangian terms. This is, I guess my motivation was based on what the Warsaw basis did. So when I have this parentheses here, those flavor representations can be unambiguously combined into a single Lagrangian term. So in contrast to this approach, you might also, it might be, for clarity purposes, you might want to instead have just one flavor representation per Lagrangian term. So if you were to do that, you would then have 4 Lagrangian terms instead of 2 here. And that's what our colleagues did in this nice paper here. And we heard a lot about that earlier in the session. Okay, so you put this all together. The result turns out to be 17 pages long. That's the only takeaway from this slide. It's a long result. No need to squint here or anything like that. Okay, so moving on from the SMEFT to the low energy EFT below the electroweak scale. So the idea is once electroweak symmetry is broken, we have some light particles and we have some particles with masses comparable to the electroweak scale. So we want to integrate out those heavy particles, W, Z, top, and Higgs. And just one other point to convey here is that this is the correct energy. This is the correct EFT at low energies, regardless of whether the SMEFT is the high energy EFT. So the Higgs may or may not reside in an SU2 left doublet, but the left is still the correct low energy EFT. Okay, so in terms of dimension-8 operators in the left, there are 4 classes of operators, and these are all present in the SMEFT. So given that I already have a SMEFT basis of operators, this makes it somewhat straightforward to construct a left basis of operators. So there's a complication that arises though, because now that SU2 left symmetry is broken, there's new types of 4 fermion operators you can have here. And I've color coded this so you can see the arrows pointing down are the new types of 4 fermion operators that are arising. So this counting is new here. And again, as previously mentioned, there was our colleagues have a paper on this topic as well, and it goes up not only through dimension 8, but also to dimension 9. So it turned out the result was only 16 pages long this time. And again, that's the only takeaway here. It's a lot of operators. A couple other topics of interest to me in the left. So the matching from the SMEFT to the left at dimension 6 is known to the 1 loop level, and at dimension 7 it's known at tree level. To the best of my knowledge, it hasn't been done at dimension 8 yet, but I just want to point out that it's quite rich in its nature. So there's much more than just contact interactions here. You can expand the W and Z propagators to second order and their propagators. Higgs exchange, because there's only light fermions left in the theory, all the Yukawa interactions are suppressed, and so they're formally of order dimension 8 as opposed to dimension 6. You could also have 2 insertions of dipole operators. You can have triple gauge insertions where a photon's coupling to 2 W's, and that gives you dimension 8 effects. So I think that that'll be quite an interesting project. And then the other question of interest to me is that, so the left, as I've been saying, is a valid EFT in its own right, independent of whether the SMEFT is its UV completion or not. And as such, it has its own positivity bounds. And so I'm curious to know what additional info might be lying around there, in particular in the case when the SMEFT is the correct UV EFT. Okay, so I'm going to move into a couple of applications now, and just as a warm-up here, so I'm looking at dimension 6. So if you stare at the anomalous dimension matrix of the dimension 6 SMEFT for long enough, you notice these patterns where certain operators can't normalize other operators. And a nice explanation for why this happens was worked out first some years back at this point. And looking at this figure here, you could state this as operators can only renormalize other operators in this table if they're in the same cell or if they're above or to the right of the initial operator. So they can't renormalize operators that are below them or to their left. And then on top of that, there's this concept not universally applicable, but it's called tree loop mixing. So this is where you assume the UV theory is weakly coupled and renormalizable, and in that case, you can classify operators as to whether they can get matched in a UV theory at tree level or at some loop level. And initially, there was a curiosity as to why there didn't seem to be much renormalization of loop level operators by tree level operators. So all tree level operators are shown in red here. Loop level operators are either in black or blue, and the loop level operators that can get renormalized by the tree level operators are shown in blue. So it doesn't happen very much at dimension 6. So I constructed the analogous table at dimension 8, and so the same thing applies here. Operators can renormalize other operators only if they're in the same cell or if they're to the right or above the original operator. They can't renormalize operators down or to the left. And so in addition to this approach to working out selection rules at dimension 8, as Xiao said in his talk, there's additional selection rules you can have from angular momentum as well. But the thing I'd like to point out here is that this tree loop mixing that seemed rare at dimension 6 is actually quite common at dimension 8. And kind of in retrospect, when you look back at it, there's just not that many possibilities here at the dimension 6 level. So that maybe just explains why it didn't happen too much there, whereas it in general seems to be a fairly general phenomenon. Okay, and so how I originally got interested in this project of working out the spaces of dimension 8 operators was kind of took a long road to get here, but a while back I was thinking about double Higgs boson production with Sally Dawson, and the question we were trying to answer is there a simple UV model that enhances the double Higgs boson production rate that's not already ruled out? So the idea here is that the double Higgs production rate is not particularly well measured at this point, but there's many other measurements that could constrain models that might put a damper on any potential explanations here. So some of the candidates we considered were extended scalar sectors, where there's new SU2 left representations. So these singlets, triplets, and quartets contribute to various processes that you could measure. So some contribute to single Higgs production. That's with the blue arrows here. Some contribute to all of them contribute to double Higgs production. Those are shown in the green. And then some of them at the dimension 6 level also contribute to electroweak precision data. And this is bad for these models. It's going to in all likelihood, limit how large of an effect they can give you in double Higgs boson production. So one application of having a complete dimension 8 basis. So I guess I'll just pause here. So right now in terms of the dimension 6 level, the quartets look like strong candidates to enhance the double Higgs boson production because that's the only operator they're generating at dimension 6. So I jumped ahead of myself a little bit there, but things are not actually so simple. Once you go to dimension 8, the electroweak precision data story becomes more complicated. So it's fairly well known that the S and T parameters are dimension 6 operators and the U parameter is dimension 8. But you can work out that there are in fact contributions at all orders at dimension 8 and beyond to the S and T parameters. So I did this in my paper back in May. I also recommend the SMEFT papers on this topic if you're interested as well. So the twist in the story is that the quartets generate the T parameter at the dimension 8 level, which essentially rules them out from enhancing the double Higgs boson production rate, which they would have otherwise been great candidates for this process. So from a phenomenological perspective, it looks like the singlet model is the leading candidate among these choices here. Okay, so that's all I had in the main part of my talk. So I just wanted to emphasize that there's many different motivations for going beyond dimension 6. And before I get too far ahead of myself, I wanted to emphasize the take home here was that So that the particular motivation for going beyond dimension 6 here is that there's a difference in experimental precision, whereas the electroweak precision data is very precisely measured and the double Higgs boson production rate is not. So all different kinds of reasons for going beyond dimension 6. There's now, and so the other point is that there's complete bases of dimension 8 operators in the SMEFT and the left, and there's methods for dealing with derivatives and repeated fields. Thanks for your attention.
Okay, thank you, Chris. Okay, so we have time for questions. Let me see if we have questions from the room. Okay, that's one.
So you mentioned in your slides that some operators have certain flavor symmetries, but how did you present your results that these flavor symmetries, these flavor redundancies are removed?
So I did, I think I did a better job presenting this in the left paper, where I explicitly wrote down what the flavor symmetry for each operator or Lagrangian term was. In the SMEFT paper, it's less clear. So this is, if you're preferring definiteness in terms of the flavor representation of your Lagrangian terms, then stacking, where am I scrolling too much here? Hold on one second, please. So if you're really concerned about what the flavor representations of your Lagrangian terms are, then stacking multiple representations together is going to convolute that, is going to obstruct your view into that. So I don't know exactly where you want me to take it there. I think in terms of like listing what the explicit flavor representations were, I did do that in the left paper. And so that could be one reason why you would prefer to do one flavor term per representation. For other purposes, it may not be necessary to break it out like that.
But if I want to use operators with some flavor symmetry, how do I use your result? Since your result didn't involve any flavor information.
I mean, there is flavor information there. I guess one thing I could also add is that I did point out each time an operator vanishes, each time a Lagrangian term vanishes, when there's only one generation of fermions in the SMEFT paper. I'm not quite sure what you're trying to get at here. I mean, you would use this basis the same way you would use your basis as well. Right. Just the flavor symmetries are not manifest there. That's all.
Okay, thank you.
Thanks.
Yeah, and also for this particular question, you can follow up on Slack. You can write to Chris if you want. Yeah.
Yeah,
happy
to take it there.
Yeah, may I ask? So I think the previous question should be reformulated in the following. So how do you confirm that the single operators you listed do have those kind of symmetries? Do have those kind of permutation symmetries. So from our experience, these kind of flavor symmetries do depend on the form of the operator or the indices of those repeated fields. For the simplest example, the Q3Q and 1L, if you mess up the indices, then you will obtain the zero. One of them would be 0.
Yeah. So one. Okay, I see what you're saying. Where do I want to go here? So one point. So this was talked about a little bit, I think. So these mixed representations here, so the two ones, the adjoint representations, if you like, for SU3, are two-dimensional representations. So given the question, I think I could rephrase the question as, given some arrangement of Lorentz indices, how do you know what are the correct gauge indices? So there's some manual work I do on this end. So let's see. So there's two candidate Lagrangian terms here that I keep in the basis, and they're shown here with these particular contractions of SU2 left indices. So that the contractions are M, N, J, K, and all the indices on the fermions are the same here. But how do you know that that's the how do you know that that actually contains these flavor representations? There's another way you could contract the indices, and I think that's what you're trying to get at. So here there's M, N, J, K. Another possibility would have been M, J, K, N in this Q, what I've called Q3 here. But here, so you have to go through and manually check if you contract the indices in this way, the operator becomes symmetric in this first bilinear of quarks. And so you can't, because it's symmetric there, this anti-symmetric, this first blue term here is going to vanish for that operator. So it'll only give you 2 of the 3 flavor terms. So that's not going to be the operator you want, not going to be the Lagrangian term you want to keep. So there's I guess there's maybe a long-winded way of saying there's some extra work you have to do to make sure you've got the flavor representations correct.
I see. Okay. Yeah, I just wanted to mention that we actually have a algorithm of desymmetrization that could help you to find these kind of monomial terms, such that it contains these definite permutation symmetries. So in that sense, for example, you said our operators gives 100 terms for the dimension 6, but after the desymmetrization procedure, actually we can get the same number of operators as in
the number of operators is going to be the same no matter what. It's just how you choose to like bucket them together.
I mean the 100 after the desymmetrization, actually we can get 84 instead of 100, which you should let me see.
Yeah, sorry. Right. Sorry to interrupt. Yeah, I think this is a very interesting discussion, and I really recommend you to follow up in Slack. And also, sorry for John. I think we probably have to move on in the session, and you can sort of really discuss there in Slack. So then we can move to the next speaker. So